And thank you for taking the time to watch another video. I know we were just meant to post one, just a rough demo on how to run the program, but I just felt like another video would clarify some things about the data set. For example, that was a bit complicated, and I did describe it in quite a lot of detail in my report, but I just felt like a video would be a bit more easier for me to describe any sort of confusion if there is any in the report. But just a little quick glance over what the data set looks like and why I set it in that specific way with the whole dimensions. Um, this diagram is in the report. Um, Basically, the data set is made of 5 different words. Now, these 5 different words, we've got the word hello, and the word my, and name, is, and Osman. So each of these words, I did keep the data set small, but each of the words are modeled 15 times by 5 speakers. That is actually 3 samples per speaker. So each speaker spoke each of the words 3 different ways. Um, a little bit higher, a little bit lower, as normal as they can say it. And each one gave a completely different result for the MFCCs, but very similar. You could detect the pattern there. Um, so yeah, you're looking at a total of 15 different solutions which fall under the word hello, and then the same thing for my. And like I said, 3 of them belong to one speaker, and then the other 3 there, and then so on. So each of the y-axis basically represents the speakers of the dataset, and then on the x-axis, you basically got them corresponding to the words. So the first 3 columns would be for hello, the second 3 for my, the third 3 for name, and then so on. Now, the reason why I chose MFCCs, which are male frequency septural coefficients, they are basically the most popular and the best way to model sounds. And the way they basically work, and it's in more detail in the report, but it's basically getting the mel bands and calculating 13 coefficients for each bin, FFT bin. And so basically for one word, you would have 13 coefficients in one row, but that row represents only a split fraction of the sound. There is an example of the what the data actually looks like, and I'm just going to quickly grab that for you there. This is just the word hello, and I know there are quite a lot of repeated values, but you do see these small little changes that do happen, show a detection of the sort of change in sound, a very small change, but a change nonetheless, and it does give information about what the word may be. And that also helps with phoneme detection, which is like phonetics and vowels. And I do describe that in my report about how I may further develop this program to specifically search for this sort of data, the small changes which give us phoneme detection, vowel detection, and it is a better way to basically optimize this whole implementation to the solution. But that's more in the report. The data is very long. It goes on for about this one, I think about 1800 to 2000, yeah, 1800 um, coefficients. That's 13 in a row. Now, these can be anywhere from 13 to 88, but I chose 13. I thought that was sufficient enough. A lot of the values are repeated, but what I did is I basically um, calculated the averages, and there is a AVG MFCC file there, and that's basically the averages of the full MFCCs. So that's basically getting all the sound, and it's sort of like a way of me warping the sound, because you do every single word is slightly different. One might be 1800, the other one might be 2500 different MFCCs. So what I do is I basically calculate the average and divide the sound into 20 parts. So at 2000, if there were 2000 coefficients, I would look at the first 100, and I would calculate the average for each 100 and then put that into one dimension. So coming back to that, and that's basically the averages there for the same word hello. And as you can see, that none of these are repeated. Every single one is unique in its own way, and that's why I feel like MFCCs were the very strong and the correct data to use for speech recognition. Now, the reason using the MFCCs, each location on the grid basically represents one of those text file of the averages, and then when we feed a solution to the search criteria, which basically sets the fitness function and tells them whether they're close or not, we're basically calculating the difference between those two files. I will get onto that in a bit of a second, but as you can see, like I said, we're splitting the sound into 20 parts to calculate the averages, and I felt like this was the best way to sort of look for those sort of phonetic patterns as well. Vowel detection, which was more of further research, but the first dimension would basically represent the first 1/20th of the sound, and then the second 20th of the sound, and then the next 20th of the sound. So we're basically breaking that sound. If it was 2 seconds long, we would break that sound into every 10 milliseconds, and then each dimension represents 10 milliseconds of that sound. So in some cases, like we got in the demonstration that I was just previously showing in the demo, I noticed this just after. You do see that in this dimension, even though the word is for the word hello, and all of these were in the right columns and they were falling under hello, over here you can see that on dimension 4, it closely matched to the word my, and all the particles managed to move to that position. So on the fourth dimension, they've all converged to my, even though the actual solution is hello. And the reason why that happened is because there could be a strong correlation at that point in time. So if it's the fourth dimension, and let's say both sounds were 2 seconds long, then we're looking at roughly 40 milliseconds into the sound. The two words have some sort of correlation in the MFCCs. And I felt like this was very important, even though it might not be doing what we want it to do exactly. I felt like this sort of data is, and these sort of clustering patterns that we might see, allow us to further develop the whole speech recognition and sort of integrate it with swarm intelligence. Excuse me. But yeah, that's basically one advantage of having it into different dimensions, as well as calculating it against the averages. But okay, and yeah, that's basically roughly what all of this data is and what the structure of the data is. And now I'm just gonna, even though I know it's been quite a while with me talking, I'm just gonna quickly go through the if you could bear with me for a couple of minutes, just quickly talk through the code. When you start it, we do have the main classes, which is what you'll be running it from if you wanted to run the demo. The main class is simply just a bunch of comments and just the face of the whole program. But getting into it, we've got a particle class. Now in the particle class, you've basically got the get fitness function there, and then each particle entity that you create from this class links to a location and it links to a velocity, and those are in these classes: the position class and the velocity class. Velocity class, we've just got getters and setters there, and we've got getters and setters in the position class too, and we've also got a constructor there that sets the coordinates, z being the dimension here, and then x and y coordinates, and that means x would be the word, y would be the speaker, and z would correspond to the point in time of the sound. Now, in the particle class, we've got this fitness function. The fitness function basically just calculates the difference between um, uh, the difference between the hypothesis of the particle, so the point in the solution space that it may be at. It will then extract the MFCC file uh, that the particle is currently at, and then it would compare that against the solution that you chose from the start, and it would calculate the fitness using the Euclidean distance um, of each single of the 13 coefficients, and it's only going to be at that dimension, so we only have to worry about 13 values to calculate the difference between, and then that difference gets passed on, and that returns the fitness of that particle. Now what's happening is we're going to basically once the fitness is passed through, we're basically going to the actual algorithm class. Before I quickly do that, I'm just going to quickly go through the tilemap class. The tilemap class is just basically the under the bonnets, extracting the way I basically model the data, extracting the files, getting the averages, and storing them to arrays, and just initializing the data, and all that sort of stuff is basically in this file. If you want to look at it in a bit more detail, I do have these sort of uh, descriptions and representations of the sound and the data file and the way I'm trying to structure it here. So a little bit of a data layout there. Yeah, a bit more about that here. And yeah, this is the function that we're calling from the fitness function. This function is basically get MFCC. It's using the x and y coordinates and the dimension coordinates, z coordinates, to find out what their coordinate represents. So it does look a bit long, but that's only repeated because remember we did have three columns, three, so that's 15 different coordinates for one of the words, and also each one corresponds to its own file. So it does seem a bit long. It was really long to kind of figure out, but I just felt like this was efficient and it worked for me. And then lastly, this last little function here is basically what we use to set the data. So when you do type in that file that you want to be searching and setting as a search criteria, it runs through this function, and it's basically setting the global function for search. And the reason why what it's going to basically do is print that file that you've chosen into this search for array, 2D array, and then we're going to constantly be making our comparisons to that to try and find it. That's basically linked to the global class, and the global class just has a few variables in there, variables which are basically set to the default variables there. These values over here belong to the update equation in the PSO algorithm, and they're basically just parameters that we use in there to to update the velocity of each particle. And by updating each velocity, we then append that to the particle's previous position, which was at let's say at iteration t minus 1, and then we would basically compute the next t plus 1, the next position, by adding on this new velocity that we calculate. I just set the parameters to this. This is probably another area of research which I did mention in the report, is how to optimize these parameters. You know, if you do tweak them a little bit, you do get different results, you do get better results, but from what I could roughly judge, that these parameters were fine. There shouldn't be too much of a change between these two weights. and the inertia rate, I basically set the bound, the difference between the two, very low, and because I didn't want there to be, um, I think it was for a localized search, but there is more detail in my report. I wouldn't go into it too much here. Now going on to the final class, which is the actual PSO algorithm class. What this does is we first start off by installizing all the particles. All the particles are given a random uh, x and y coordinate, and they are given a random velocity. Dimension here isn't random, and that's just because what I've done here is I've basically set a nested for loop to go through the population size, the swarm size, and divide that by the global dimension. So what we're doing is we're basically sticking all these other random velocity and x and y coordinates under, first of all, we're going to go through dimension 1, dimension 2, dimension 3, all the way up to dimension 20 until we until we've installed all of the particles at a random location. Now that then passes through to the particle class, and if you remember, the particle class goes through, installs all these variables to the position class, and then to the velocity class, to the getters and setters for that particle. Now the next function, which is the only other function, is execute. Now what execute does is it basically brings everything together, and that's the only thing that we call in the main method. We create an instance of the PSO algorithm, and then we just call execute. By calling execute, it does that for us. It initializes the particles, which is the method above, and then we go on to the to going through the max iterations. And first off, we calculate the fitness of all the particles at their own random locations, and then as the iterations progress, we carry on calculating the fitness, and then we compare the fitnesses here. We compare the fitnesses, and then we update the particle's best fitness. So each individual particle's best fitness, which is stored into its own array, and then we calculate the G best. And now, even though I put down G best, the reason why I put down global best particle is because I wanted to make it seem, even though it is local, I wanted to make it seem like it was global and separating all the dimensions. Basically, even though they should only be one, it's actually, because the data is being split into 20 parts, I've basically got 20 different G bests. So they're basically 20 local bests, one best solution per each dimension, basically. And I just set it to a random 100, and then after that, from then on, after it's initialized, over here is where they update the P best and we update the G best on each dimension. Now, this is the important part, I'd say. This is what the update algorithm for the PSO is. First, we start off with the weight. This interior weight, like I was saying before, by setting the upper and lower bounds close together, we're looking at a more localized search, which is what we want, because we're not letting the particles change in velocity to go between dimensions. They are only staying on their dimension. So yeah, this is just basically a very small number for the weighted mean that gradually closes in. So I did keep the two upper and lower bounds together, but it does get smaller, and that contributes to kind of gradually slowing down the velocity in a way. Getting on to the actual algorithm that's right here. This is the actual PSO update equation. And the way it works is we've got two random variables, R1 and R2, which we've installed over here. We're going through each swarm in each particle in the swarm. We're getting their locations, x and y. We're getting their velocity. We're getting the particle best, the G best, and then we're just basically passing it through this PSO update equation. The equation is described in detail on the in the report, but that's basically what we're doing here. We're basically following that equation here. That is referenced at the end of my report in the tables and equations section. And yeah, we've then got a new velocity for the x and y, which is what the equation does, and we just simply append it to the new x and y position, and that is pretty much it. We set the new location for the each particle, and we're done here. Um, so I know I went on for quite a bit. I don't even know if you actually managed to watch it all till this far. If you have, then thank you so much for being patient with me. You really didn't have to carry on watching, but I really do appreciate it, and thank you for taking out your time to carry on watching it. Um, well, yeah, thanks for watching. Hope I didn't ramble on too much, and all the best. Thank you.